we've got 5 switches and they can either be on or off, and we're asked in how many different ways can we have the row so that no two adjacent switches are in the off position. So I'm going to say that on is a 1 and off is a 0 rather than having to write the words down. Okay, so what I can't have is something like 1, 0, 0, 1, 1. That's not allowed because then I'd have two adjacent off switches. So let's take a look at some different situations. What about if we have 0 off switches? Then I'd simply get 1, 1, 1, 1, 1. There's only one way to do this. One off switch, I could have 0, 1, 1, 1, 1, or I could move the 0 to every single possible place, and there's 5 places. So there's going to be 5 ways we can do it. 2 off switches is going to be the most complicated, so I'm going to come back to that. 3 off switches, actually there's only one way. 0, 1, 0, 1, 0, and that's it actually. Okay, this takes us to 2 off. By the way, 4 off would definitely end up with some adjacent, so we don't have to look into that as well as 5 off. Okay, 2 off, I'm going to work through these systematically. Let's say that the first one is off, then the second one can't be, but I could have the third one as off. Let's keep the first one as off, and then move the next off one to the 4th position. You can see I'm systematically working my way through this. So that is all the possible ways where the first switch is off. Okay, now let's have the first switches on then and put the second switches off. Then I can either go 1, 0, 1, or I could have the second one off and then go 1, 1, 0. Okay, let's have the first switch on, the second switch on, but the third switch off. And then it would have to be 1, 0. And that's going to be it for the third switch off. If I go with the fourth switch off, then I'm going to end up with some of the earlier switches having to be off as well. And so I've actually already counted them. That is it. So very carefully, I've figured out that there are 6 ways that I could have 2 off switches. So if we add all of these up, then overall, there's going to be 13 ways to do it. Really nice question. Gets even better because in the solutions, they say it's left as an exercise for the reader to show that if there are n switches, in fact, the number of different ways follows the Fibonacci sequence. It's just when n is 1, we're going to get 2. When n is 2, we're going to get 3, 4, and 5 for 13. So that's actually the one that we found. How can we show that it is generally true that it's going to follow this pattern? So pause the video and try this out. This is harder than the actual JMC question by far, but it actually has a lovely and in fact quick solution. So I'm going to go through it. I'm going to assume that you've had a go or you just want to see how it can be done. So for one switch, we could either have it off or on. You can see there's our 2 ways. 2 switches, either 0, we can't have 0, 0, so 0, 1, 1, 0, or 1, 1. I'm just kind of showing how the pattern gets started. 3 switches, then it's going to be 1, 1, 1, or could have 0, 1, 1, or 1, 0, 1, or 1, 1, 0. So this is with no zeros. This was 1, 0, or we could have 0, 1, 0. That would work. So we can see that there are 5. Let's deal with 4, of which there's going to be 8. So 1, 1, 1, 1. Then again 1, 0. How we can work for it systematically. Then 2 zeros. And is there any other way? Oh yeah, we could have 0, 1, 1, 0. So that will give our 8 in total. And of course, in the question, we've got our 13 ways that I showed before. Now I'm going to show you another way how we can get 5 switches, and it is going to result from just adding these together, because that's how the Fibonacci sequence works. We're just adding the previous two terms. So once we've started off with the Fibonacci sequence, of course, we're kind of ignoring the 1, 1 because our first term was 2 and then 3 and 5, but we can see that the Fibonacci sequence is starting off. So if we can then show that we always just add the previous two terms together, then we can see it's going to carry on forever, and we can be 100% sure we will generate the Fibonacci sequence, albeit shifted slightly. So an alternative way for 5 switches, well, we've done it with 4 switches. So imagine just essentially adding another switch. We've got our 4 switches and we're adding another switch. Now, it's either going to be a 0 or a 1. So first up, we're going to make it a 1. If we make it a 1, then we can then turn this problem into all the different ways of having just two, making sure there's not two off switches adjacent in the remaining 4. And so that is where this 8 is going to come from. There's going to be 8 ways of showing this. So I just want to say that again, with the right switch being a 1, we can then use the 8 solutions for the 4 switches to guarantee that there are always 2 apart. Sorry, that there's never 2 off switches that are adjacent. Okay, now we can just look at the case where the right switch is a 0. If the right switch is a 0, then that means the one next to it is going to have to be a 1. And now I've turned the problem into how many switches are there, well, how many ways are there when there's just 3 switches? And that's where the 5 is going to come from. So we can simply do 5 plus 8 to give 13. And that's it. That's how it's going to carry on forever, because you're just adding an extra switch, and then you basically, if it's a 1, it just becomes the case prior. If it's a 0, you have to put a 1 in, and it becomes the one that's 2 cases prior. So let's look at 6 switches just very quickly. 6 switches, you're going to have your 5 switches from before, and then your 6th switch. Well, in the first example, let's just say there's a 1 there. Then we've got all the different ways we could do it for 5 switches, of which there's 13. And then what if there's a 0 as our last one? And there's going to have to be a 1 there, and then it's the 4 ways. There's different ways for 4 switches. So 8, and that's how we know it's going to be 21. And then the next one, you would just do 13 plus 21 to give 34. And it's basically a domino process. It's actually a form of proof by induction. Show it's true for 1 and 2, that you get certain numbers. Then show that you're just adding the 2 terms together to get the next one. And continuing to do this, and you'll generate your Fibonacci sequence. So I hope that makes sense. I just thought that was a really lovely additional question to this problem, and the proof was amazing as well. Really enjoyed this question. Hope you did as well.